Hello, I welcome you all to this another interesting screencast. The problem reads, determine the maximum force P that can be applied without causing the 250 kg crates to move. The coefficient of static friction between each crate and the ground is mu s equal to 0.25. Right, so this problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So we are dealing with dry friction. And this is a force that resists the movement of two contacting surfaces that slide relative to each other. Alright, and the maximum friction itself is defined by this equation, F equal to mu times N, where mu is the coefficient of friction and N is the normal force. So we are going to encounter three types of problems, three types of dry friction problems. Okay. So the first one is the experience. The first one states that there is no impending motion at the points of contact or the contacting points or the contacting surfaces, and this simply means the number of unknowns are less than or equal to the equations of equilibrium. Okay, number of equations of equilibrium. All right. So it simply means we're able to solve such a problem using just available equations of equilibrium. And for such a case, after solving, we need to check the point of contact or the contacting surfaces to see whether this is met, this equation. And if this is met, then we are sure that there is no slip at the contacting surfaces. The second one, this is where we have impending motion. We have impending motion at some points of at some contacting points or surfaces. So we have some motion, and in this particular case, the number of unknowns are greater than the number of the equations of equilibrium. Okay, and in such a case we need to use the friction equation also. Okay, so in such a case we need to use the friction equation. And then in the third case, of course, this is where the impending motion takes place at all contacting points or surfaces. This is where we have motion at all points, impending motion at all points, okay. So in this particular case, again, we employ the same condition, which is number of unknowns are greater than the number of the equations of equilibrium. Therefore, we invoke additional equations from the friction equations. The second and the third type of problems here, we need the correct direction of F in our free body diagram. We need the correct direction. Here we are free to assume the direction. We are free to assume the direction, okay, of f. Even when you assume the wrong direction, you are going to get a negative, which simply means the direction that you had assumed was not the right one. Instead, it is the opposite. So only in case one, this is where you have the option or you have the freedom to assume. But in case 2 and 3 or problems 2 and 3, there we don't have the option. We need to assume the right direction. Okay. So basically these are the three types, and in short this is basically what we're going to do for all the problems we're going to solve in this particular chapter. Okay. Right. So let's draw the free body diagram. So let's say we have the weight there like so, and another one there going through the centroid. Okay, and let's say we have friction. So we say friction is in opposing this direction. So let's say it is somewhere here. Okay, and then we have another one somewhere there. All right. Okay, and then what else? Let's say we have the normal force. We have the normal force somewhere there. We have the normal force here. Okay, let me just move this a little bit. Let me move them, maybe doesn't matter really. I just want it to be there for me. Okay, and also I place that one like so. And let's say I have my normal force somewhere there like so. And for this one I have my normal force like so. Okay. Let me just draw this line from there to here like this. Okay, and also this one I draw like so. Alright, so let's say this one there, and also this distance there like this. Alright. Something like so. Okay. And then we section this. So we have a tension force, of course, that cable like so. And then we have components of this force like so, and also like so. Right. So let's label this. So the W's are the same. Alright. And let's call this as N. This is N. This is the normal force NB. And this is FB. Let's call this as NA. And this is FA. And let's call this as T. And this is same T this side. And let's call this one as XA. This one as XB. Okay. Right. Great. So here we are. And then this one here, let's call it as P cos 30. This one as P sine 30. Alright. So here we are. We've labeled everything. This is our free body diagram. Of course, we don't expect to find XA and XB because we don't have dimensions, but they are part of unknowns for such a case like this. So how many unknowns do we have? Let's say number of unknowns there are how many? This is going to be equal to 1, 2, 3, 4, 5, 6, 7, 8. So there are 8. So this is XA, XB, NA, NB, FA, FB, NT, then P. 1, 2, 3, 4, 5, 6, 7, 8. There are 8. And then number of equations of equilibrium. How many are there? For each one there are 3. For this there are 3. This there are 3. This is a 2D. Okay. So in total how many? In total we have 6. So we are short of how many? 2. We can only solve the number of unknowns when the number of equations are equal to the number of unknowns. So we need to invoke 2 more equations here. So we need one equation, the friction equation, where I will say Fa is equal to mu Na, okay, which is just going to be equal to mu S, of course. Alright, mu S Na, which is just going to be equal to 0.25 Na, and Fb will be equal to mu S Nb, and this is 0.25 Nb. Alright, so let's find W. W is just equal to mg, that's 50 times 9.81, and this just gives us, where's my calculator? This gives us, that's a 50 by 9.81, gives us a 490.5. So I think we have all the necessary and the other thing that I need to mention is a case like this one. This one is called, so we have what is called impending motion. We expect impending motion at contacting surfaces for crate A and B. Alright, so let's start crate A. Equations of equilibrium, crate A. Let's go for crate A. Okay, so we start with summation of forces in the x equal to 0, in this direction being our reference. So we have a minus Fa, a plus T equal to 0. Okay, then we have summation of forces in the y equal to 0, going up in our reference. So we have Na minus W equal to 0. Okay, then we have another equation here, which is friction equation. Fa is equal to mu, which is 2.25 times Na. Okay, so if we are to feed this equation here, if we are to feed this equation there, okay, realize that our value of T therefore will be equal to Fa, which is equal to 0.25 Na. Okay, and then we also know what Na is. Na, we feed this Na here, okay. W already calculated, we said our W is equal to 490.5 newtons. Therefore our T is just going to be equal to, that's 0.25 by 490.5, right? So this gives us a 122.625. Alright, that's 0.25 by 490.5, 122.625. Okay. So we know what T is. Let's go to crate number 2, which is crate B. Crate B, summation of forces in the x direction equal to 0 in this direction, like so. So we have minus T minus FB plus P cos 30 equal to 0. Okay, then we have summation of forces in the y equal to 0, going up in our reference. So we have NB minus W plus P sine 30. Okay, equal to 0. And then we have another equation, which is the friction equation. FB is equal to 0.25 times NB. Okay, so what we need to do now, we need to create two equations for NB. So let's say we feed this here, here like so. Alright, and once we do so, then we are going to have the following. Let me create a boundary here. I create a boundary. Alright, so once we do so, then we are going to have the following equation. We'll have the following equation. This is minus T and this is FB. So we'll say our P cos 30, minus FB, and our FB will be 0.25 NB. And mind you, here we already calculated what T is. We said T is equal to 122.625 newtons. Okay, so our T will take it the other side, so we'll say 122.625. Okay, and then we have this other P there, P sine 30 plus NB is just going to be equal to W, and W is just a 419.5. So we have these two equations that we just need to solve simultaneously. So what I'll do is I'll get rid of n there, so I'll multiply this side and the other side. I'll multiply this, I want to use substitution here by I'll multiply this side by 1. Sorry. Okay, I'll multiply here by 1. Okay, coefficient of NB there by 1, and then here by 0.25. And I'll add. Okay. And then once I add, then I'll have the following. Let me just do this. I'll have the following. So here I will have P cos 30. So let me add them. Let me add them in advance. So this will be P cos 30. P cos 30 plus 0.25 P sine 30 equal to 122.2625 plus 0.25 by 490.5. Therefore, our P is just going to be equal to, let's work it out now. You can work it out, right? So 122.625 plus 0.25 times 490.5 divided by cos 30 plus sine 30 is 0.5 by 0.25. Okay, like so. Okay, so this gives me a 247.47 newtons. Let me just repeat it. So 122.625 plus 0.25 times 490.5 divided by cos 30 plus 0.25 times sine 30. So 247.47. Okay. So therefore, since this is what we wanted, so we'll say our P max, our value of P max, okay, that we need to apply without causing the two crates to move is equal to 247.47 newtons. Okay, I think we are done. So let me just outline the final solution. I outlined the final solution. So we have P max. P max. This is what we wanted to find. You can go and check out the value of N, NB, and NA, but it was not part and parcel of the problem. You can check them out later on. So I hope this particular video was helpful. And if it was, give me a thumbs up. I like my video. Continue subscribing and liking my channel. Bye bye, and see you in my next screencast.